This program is a presentation of UCTV for educational and non-commercial use only. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
This iconic picture from a former colleague of mine, Professor Keeling at the Scripps Institution of Oceanography, shows the seemingly inexorable rise in carbon dioxide in the atmosphere over the past 50 or so years. And he also started looking at the seawater off Hawaii and showed clearly that you could see also the gradual decrease in pH associated with that we've come to talk about as ocean acidification. And in essence, when we talk about ocean acidification, we often explain it rather straightforwardly. And so I'm going to do that first, and then as we go further into it, you'll see that it's not necessarily quite that straightforward. CO2 goes into seawater, reacts with water to form bicarbonate ion. But in addition to forming bicarbonate ion, we get some extra hydrogen ion, which goes on to react with carbonate to form still more bicarbonate. In essence, this reaction, that you're increasing this dissolved CO2, it's reacting with the carbonate, decreasing that, increasing the bicarbonate. The change in hydrogen ion concentration is almost a side effect of those changes in carbonate species concentrations. And also, because the carbonate ion concentration decreases, the saturation state of calcium carbonate decreases. The saturation state being defined in this fashion, essentially the ratio between the concentrations that are in seawater with what they would be if it were at equilibrium, the equilibrium solubility product. And as I note there, one can think of calcium carbonate saturation state as a measure of how easy it is to form a shell. It's got a more technical chemical meaning, but as a biological process, that's probably the easiest way to think about it. So as we go on and look at the changes we're talking about, these are really the two key features. Ultimately, once you know about CO2 chemistry, you'd like to say, okay, if we do increase the CO2 in the atmosphere, how much would the pH in the ocean be expected to change? How would you calculate that? Or what would the consequence change in the saturation state of one of the forms of calcium carbonate, aragonite, be? Would this be the same all over the oceans? And then really, for your experimental purposes, perhaps one of the more important pieces, and this is really the content of most of our second lecture today, how would you go about measuring what was in a sample of seawater? And planning an experiment. How would you modify the chemistry of a sample, composition of a sample of seawater to be the composition that you wanted to inflict upon your organism? So, where should we begin? As I've said, there's a lot that I'm leaving out here. Really, I'm going to talk basically with a brief introduction to carbon dioxide equilibria in seawater. And I'll talk a little bit about the things you can measure in seawater so that you can see just how it's changing as you modify the composition. But these are not separate pieces. The acid-base equilibria in seawater, the analytical measurements, and the desired results kind of all feed together one on another. You can't easily separate them one from another. I wrote for this handbook Guide to Best Practices for Ocean Acidification Research, a chapter on the carbon dioxide system in seawater, and you should be able to download that from the EPICA website if you want to read it. Much of what I'm going to talk about today is covered in that chapter, some fragments perhaps less so, some fragments more so. But as a good introduction, this exists. So, acid-base equilibria in seawater. There's a whole variety of possible acid-base systems in seawater, of which the carbon dioxide system is by far the most important, but certainly not the only one. The water itself is, of course, an acid-base system. There's also boric acid in seawater. There may be ions such as the nutrient phosphate, which can be present in various acid-base forms. There could be organic acids that you don't really know what they are, but they're still there and affecting the acid-base chemistry. So it's not just carbon dioxide, but we're going to focus on carbon dioxide and then indicate how the others affect that. So carbon dioxide equilibria in seawater. The first thing to recognize is that one of the things is gas solubility, where we have an equilibrium between the composition of a gas phase and what's actually present in the aqueous phase in the seawater itself. And this is represented by an equilibrium constant, the solubility constant, which relates the concentration of the aqueous CO2 to a measure of the concentration in the gas phase, that product of mole fraction and total pressure is essentially the partial pressure of CO2 in the gas phase. So what this essentially says is that as you change the concentration of CO2 in the air above seawater, if it's at equilibrium, you also change in proportion the concentration of unionized CO2 in the seawater. The complexity with CO2 is that in addition to being a gas, it's also an acid-base system. And so the CO2 itself can dissociate, reacts with water to form hydrogen ion and bicarbonate ion. And the bicarbonate ion can also dissociate, again to form hydrogen ion and carbonate ion. And these two, again, have equilibrium constants relating the concentrations of the species, where this term H+, throughout my presentation, I will be talking about as the total hydrogen ion concentration. Suffice it to say that there are many ways you could define a term like that. Essentially, it's related to what we think of as pH. But as this is indeed the short version, we will do without that hour and a half of lecture. You'll be glad to hear. So the relationships between concentrations is really the key factor involved in equilibrium chemistry of CO2 in seawater. There's a variety of possible things that you could measure, and I'm just going to list these quickly so that they're familiar in your mind as we go on. The first, the total dissolved inorganic carbon. This, I've written it as carbon total. Other people often write it as DIC or TCO2, sometimes the Greek sigma for some of the carbon species. It's basically the total concentration of CO2 present in the seawater as CO2 species, that is, the CO2, the bicarbonate, the carbonate. It's usually measured in units of moles per kilogram of solution. The moles are obvious. Moles are a standard chemical unit. Per kilogram of solution, the convenience of that is that it makes this term temperature and pressure independent. Thus, if you take a sample of seawater from the deep ocean, where it might be at 3,000 meters depth and at a temperature, let's say, of 2 or 3 degrees centigrade, and you bring it up to your ship where you actually make the measurement, but now you make it in the lab where the pressure is just atmospheric pressure and the temperature is a good deal warmer than 3 or 4 degrees centigrade, but depending upon where you are, somewhere between 20 and 30 degrees centigrade. Nevertheless, you're measuring exactly the concentration that was present in the deep water. Of course, the proportions of these change as you change the temperature and pressure. They change because those equilibrium constants that I showed you previously are each functions of temperature, pressure, and also the salinity of seawater. So for a sample of a fixed salinity, the change is simply due to the changes in temperature and pressure. Total hydrogen ion concentration, or pH. pH is defined here minus the decadic logarithm of the hydrogen ion concentration, or the decadic logarithm of the reciprocal of the hydrogen ion concentration. Why? Who really knows? It was written first that way over 100 years ago, where the logarithmic scale was convenient for the large range of concentrations that were being used. The decision to choose the reciprocal of the hydrogen ion concentration rather than the hydrogen ion concentration itself is lost in the mists of time. Nevertheless, this is how it's done, and you might as well remember. Lower pH numbers, more acidic. Higher pH numbers, less concentration of hydrogen ions. This pH, as it's a logarithm of something, is necessarily a dimensionless quantity. However, the thing it's a logarithm of is not dimensionless. It too is in moles per kilogram of solution. Strictly, I should have written this as the ratio between the concentration and the units so that it ended up as a number, and I could take the logarithm of a number. Now, this is the concentration of an acid-base species. In the same way that each of these concentrations were temperature and pressure dependent, this concentration also is temperature and pressure dependent. Thus, if you measure the pH of a sample of seawater and you change its temperature, it will have a different pH. If you change the pressure, it will have a different pH. Another advantage of the temperature and pressure independence is if you mix two seawaters of different total carbon, you can tell simply by the proportions of the mixture and the total carbon of the individual parts what the mixture's total carbon will be. This doesn't work for pH. You can't just mix two solutions and say the average will tell me what the pH is. It won't. It may be somewhat close, but it certainly will not be accurately so. And the last CO2-related acid-base measurement that's really commonly made is referred to as the partial pressure of CO2. I alluded to this when I talked about solubility, and strictly, people talk about the partial pressure of CO2 or the PCO2 of a water. It's a property of the seawater. But really, it's also the property of a gas in equilibrium with that seawater, of an air in equilibrium with that seawater. So more strictly, you should say that it's the partial pressure of CO2 in air that is in equilibrium with the water sample. Here, PCO2 would be the mole fraction times the pressure of equilibration in that gas that's in equilibrium. And therefore, you can see the PCO2 is directly proportional to this concentration. And the constant of proportionality is the solubility coefficient, K0. Again, as this is a single species, it's temperature and pressure dependent, and the units for PCO2 are always pressure units, usually microatmospheres. When somebody says the PCO2 of seawater is 400 ppm, they are committing, at the very least, a faux pas. Possibly they don't really even know what they're talking about. PCO2s are pressure units. And the key is this relationship here. The seawater has a particular PCO2. If you equilibrate it with air at a total pressure of 1 atmosphere, then indeed, numerically, the PCO2 would equal the mole fraction if microatmospheres and parts per million. But you could just as easily have equilibrated it at a pressure of 2 atmospheres, in which case this mole fraction would be half as much, because the PCO2, being a property of the water sample, would barely have changed. Remember, I did say it was a function of pressure, and it is. But changing from 1 atmosphere to 2 atmospheres is a very small absolute change in pressure, and so the actual concentration of CO2 and the actual value of the K0 hardly change at all. So these 3 parameters are things you measure directly that relate to the CO2 equilibria. We'll introduce later one further one, total alkalinity, but for now we won't go there. So what I'm going to take a little bit of time now to do is talk about the way that you can think about the relationships between the concentrations of the various species present in seawater in a way that may make sense to you. I hope it does. We'll see at the end. Essentially, we can think about these relationships on this plot, where I'm plotting the carbonate ion concentration against the dissolved unionized CO2 concentration. And as you'll see later, 2 degrees of freedom, such as are represented on an XY plot, is quite sufficient for a complete description of the system. Well, first, these 2 possibilities. First, the red. If we're going to put any actual values on this plot, we have to specify a salinity and temperature, because all these species are functions of salinity and temperature. Implicit in all the discussion I'm doing now is that we're talking at 1 atmosphere. This is a convenience for talking about it now, but probably a realistic one, because most of your experiments are probably done in the laboratory, not in pressurized seawater containers. And most of the concern for ocean acidification is the change in composition of surface seawaters as a result of taking in CO2 from the atmosphere. So that pressure of approximately atmospheric pressure is the most important. First thing we notice is that this scale here in PCO2, of course, is directionally proportional to the scale in CO2. And the constant of proportionality given up there as the equilibrium constant. The green line is the point at which the saturation state of the calcium carbonate form aragonite is equal to 1. If you recollect this formula, essentially we're saying that the saturation state is proportional to this formula. Well, the calcium ion concentration in seawater essentially depends upon the salinity. The solubility product upon the salinity and the temperature and the pressure. Thus, essentially, this omega is proportional to the carbonate ion concentration, and although this is 1, twice as high would be 2, 3, 4, so on. So this, you can imagine the position at which you know the saturation state. The pH. You actually know the pH directly in terms of these 2. One can look at this equilibrium constant. This is the equilibrium constant essentially for saying CO2 plus water goes to 2 hydrogen ions and carbonate ion. Just going straight through that sequence of acid-base equilibria. Thus, pHs are straight lines on a plot like this. Well, first, immediately here, you see one of the problems. If somebody gives you a seawater sample and says the pH is 7.9, in principle, it could lie anywhere along that line for composition. Telling you the pH by itself doesn't tell you enough. You have to have at least 2 pieces of information. So when you say, I've adjusted my seawater to be a pH 7.6, well, that could be anywhere along that line. Without more information, you don't know enough about the composition of the water. Equally, we could do this plot in terms of carbonate and CO2 and just plot contours of bicarbonate ion. The equilibrium constant relating them is this one, and this is the equilibrium constant for that very first chemical equation I showed you of CO2 reacting with water and carbonate ion to give bicarbonate. Immediately looking at this, those of you that are familiar with typical magnitudes of CO2 variables in seawater will recognize that the concentrations here are far too high for typical seawater, with bicarbonate levels, let's say, of 5 millimolar, 5,000 micromolar. And this becomes a little clearer if instead I plot total carbon. So your seawater range of total carbon is typically between about 1900 and maybe about 2500. So seawater itself actually just fits in a band on this picture. So consequences of CO2 equilibria. First this, that in a system at equilibrium that's got both a gaseous and an aqueous phase, the state of the CO2 system is described by knowing the PCO2 in the gas phase and also all these concentrations. You have to know them all to have a complete description of what's going on. But there are relationships between those various concentrations. When a system's at equilibrium, we're essentially saying there are equilibrium constants present that relate concentrations. So this unionized CO2 in the water is related to the PCO2 in the gas phase. The hydrogen ion concentration bicarbonate and CO2 are related to each other because this particular product is a constant which is a function of salinity and temperature. Similarly for the K2. This is the key part. There are thus only 2 degrees of freedom. You can only vary, out of these 5, you can only vary 2 of them independently. Once you change 2, all the others, the values are fixed. So that if we go back to these pictures, you see that if the 2 we're varying are carbonate and CO2, then the pH is fixed. The bicarbonate concentration is known. The total carbon is known. The PCO2 was known. The omega, the saturation state, also known. So that this is potentially a problem, I think, if you're imagining an experiment on an organism. I have heard, when speaking to biologists, people say, oh, that depends upon, such and such an organism depends upon the CO2 concentration in the seawater, the PCO2. Its photosynthetic ability depends upon the PCO2. Well, yes, maybe. How would you know? Because you may know the PCO2, but if instead, and one of the other options is discussed, that somebody says, but it's the bicarbonate that it's taking up, then at this point here, we have a known PCO2 and a known bicarbonate. I cannot change easily. I can change the PCO2 and keep the keep the PCO2 constant, but change the bicarbonate by simply going up that line. But essentially, I have to substantially change the composition of the water away from that of seawater. And so these experiments are not done in anything approaching a natural seawater to do this. This is probably in part why many of the physiological studies you see on organisms go over far larger ranges of CO2 chemistry. In part, I think it's for the convenience of doing it. But the feature is you can't say, aha, it really matters what the carbonate ion concentration is and what the pH is. Well, if you matters what the carbonate ion concentration is and what the pH is, everything else is fixed. You can't vary more than two things at once. And so as you start to think about the CO2 system, this is probably one of the more important aspects, recognizing that you cannot set up a seawater where the carbon dioxide, the bicarbonate, and the carbonate are independently controlled for concentration. If you control two, the third one is fixed as to what it has to be, whether you want it that or not. And that's always the difficult part. And the other part, of course, which is, I've not said, but it's fairly apparent from this picture, is that there's always a lot more bicarbonate than there is any carbonate or CO2, simply because of the form of equations within this pH range. If you go, essentially, if you're in the pH range between the two equilibrium constants, that is, between a pH of 6 and a pH of 9, bicarbonate will always be the dominant species. If you want to go to pHs above 9, then you can get carbonate to be the dominant species. pHs below 6, CO2. Neither of these are really very realistic, particularly in a seawater environment. So people don't typically go there. So there are only 2 degrees of freedom, and you can only alter two independently of one another. So let's just talk a little bit. We talked a lot about CO2, and I mentioned at the beginning that there were other acid-base systems in seawater. Do those change this mantra or not? Well, one of the first you should consider perhaps is water dissociation itself, where you can have an equilibrium where water dissociates to give hydrogen ion and hydroxide ion, and again with an equilibrium constant, the Kw, which function of salinity, temperature, pressure. So we've already said with 2 parameters we knew hydrogen ion. So if we know hydrogen ion and we know this equilibrium constant, we know hydroxide ion. So there's not much more there, except we had to have one more piece of information, the additional equilibrium constant for water itself. Probably the most significant acid-base species in seawater, in addition to the carbonate system, is boric acid. It's about 20% of the total concentration of CO2. So CO2 concentration perhaps around 2,000 micromoles per kilogram. Boric acid around 400 micromoles per kilogram. Again, boric acid forming hydrogen ion and borate ion and an equilibrium constant. So if we know the equilibrium constant, we've added essentially 2 new species. If we know the equilibrium constant, we still have added 1 degree of freedom to this. How do we cope with that? Well, one of the very convenient factors is that the total dissolved boron, that is the sum of these 2 concentrations, is a function of salinity. And so, again, we know 2 additional things. We can explain 2 additional species concentrations with the hydrogen ion concentration, which already we discussed. So again, we haven't really added that much. We've said, okay, instead of with 5 we knew 3, therefore there are 2, we said with 7 we know 5, therefore there are 2. Or with 8 we know 6, therefore there are 2. And in essence, this is the key. For every additional acid-base system that you add, you also need to know the equilibrium constants appropriate to that acid-base system, and ideally, or most conveniently, the total concentration. So if we're talking about the phosphoric acid system, which has 4 separate acid-base species, H3PO4, H2PO4-, HPO4-2-, and the phosphate ion PO4-3-. There are 3 equilibria there between those species, and in addition, the total phosphorus. So 4 new species, but 4 new pieces of information needed. If you don't know the equilibrium constant or the total concentration, essentially you're stuck about describing that acid-base chemistry. Does that matter? Not if you're interested in the CO2 system, and if you've either measured pH or total carbon or PCO2 as the measurements, because then you still get all the information you had about the PCO2, because for this additional acid-base system that you don't know, it will potentially influence the hydrogen ion concentration, but that's already built into what you know. And essentially the hydrogen ion concentration is proportional to the ratio of the acid and base forms of each acid-base pair. Sometimes you will see people talk in textbooks about pH as a master variable. And the essential idea is that as you change the pH, the ratios of the acid and base forms change. Strictly, that's backwards. You can't just change the pH. It can't be done. So what the pH is telling you is what that ratio is. And that's probably the better way to think about it. So where do all these acid-base things come in? They come into one other item you can measure, the total alkalinity. And often you'll see the total alkalinity written by this expression. It's bicarbonate, 2 carbonates, a borate, a hydroxide, minus H+. And again, it's usually measured in moles per kilogram of solution, and it's measured by an acid-base titration. You work out how much acid your seawater sample takes to titrate all these species. It has a very useful and interesting property. It's temperature and pressure independent. Now, I'm not sure about you, but certainly my first glance at that was, how in the hell could that be so? Because every one of these species is temperature and pressure dependent. It's not like total carbon, where at least you can say, well, yeah, I'm keeping track of carbon atoms. I know what's happening here. I can see that if I have a closed system, I don't gain or lose any carbon atoms. So really, one of the interesting questions is, why is this particular sum of species independent of temperature and pressure? Well, I think it's fair to say that that too could be another hour and a half worth of lecture. So we'll just kind of cut it down to the minute and a half and see if that's sufficient to help. Essentially, what this is trying to keep track of is hydrogen atoms. Only it does it in a rather confusing and convenient way. Confusing because clearly these aren't all the hydrogen-related species, and minus and plus, I mean, how do you keep track of chemicals? What's minus a concentration of a chemical? A negative concentration. Essentially, it's keeping it relative to some arbitrarily defined zero, where the zero is defined so as to make it convenient. In particular, one of the things you want to define out of this completely is water. Because in the water, in seawater, there's about 55 moles of water. So there's 110 moles of hydrogen ion. If at the same time you're looking at this particular species, which pH 8, around 10 to the minus 8, you can see that we're 10 orders of magnitude different. And that's not a convenient arithmetic problem to cope with. So you say, we're just going to define alkalinity relative to pure water. That means hydroxide is where pure water has lost one proton. Hydrogen ion is as though pure water had gained one proton, hence the sign difference between those two. We should add in other zero species. CO2, we've lost one proton to get to this one, we've lost two protons to get to there, hence the 2. Boric acid, we lose one proton to get to there. Why is this convenient? Because at the point where you titrate to, the equivalence point, you say, would be a solution that was that which you would get if you just mixed water, CO2, and boric acid. So it's enough, the alkalinity is enough acid to get you to CO2 plus boric acid plus water. Does that necessarily explain this? Maybe. If you feel comfortable that by forcing it into being a mass balance equation, no matter how seemingly grotesquely forced, it makes sense. But there is one other way to think about it that perhaps is a little more obvious to follow through. If you think of a sample of a very simple seawater that contains all these species, plus of course the ones I mentioned, the water, the CO2, the boric acid, but also the cations, sodium, magnesium, calcium, potassium, and the anions, chloride and sulfate. The sum of the positive charged ions, sodium, magnesium, potassium, calcium, and hydrogen ion, must equal the sum of the negative charged ions. You're going to have a neutral solution. It's not going to be a positively charged solution or a negatively charged solution. So it's hard to see that, but rearranging that in your mind, this sum here is actually equal to the difference between sodium plus 2 times magnesium is a doubly charged cation, 2 times calcium plus potassium, minus chloride minus 2 times sulfate. Of course, all those 6 pieces, sodium, magnesium, potassium, calcium, chloride, sulfate, are each individually independent of temperature and pressure. So that particular combination must be independent of temperature and pressure. And this is that combination. So in essence, it's a mass balance equation, or it can be thought of as related to charge balance. Either way, these are things that are independent of temperature and pressure. But it has one other particular facet that is really convenient to think about when thinking about CO2 chemistry in seawater, and it's this. If you add CO2 to seawater, you do not change the alkalinity. Again, I'd say that that's not necessarily obvious because you will change the bicarbonate and carbonate. We saw that. And if you do that, you change the pH, which will change this and this and this. So everything in that alkalinity term will change, but the total won't when you add CO2. Well, again, you can go back to my comment that it's the cations, sodium, magnesium, potassium, calcium, minus chloride, sulfate, the anions, and say, add more CO2, makes no difference. Take CO2 out, makes no difference. Add sodium bicarbonate, aha, we added sodium. Alkalinity had to go up. You could fudge this by looking at that and set this whole equation and saying, hey, no CO2 in it. Clearly, adding CO2 won't make a difference. That's not an ideal way of thinking about it, because there are ways to confuse you in that. Probably you won't come across them, but it could be done. The real key is this, that it's not changing the alkalinity, adding the CO2. Well, not much. Because if you add CO2 to seawater, then of course, if you had 1 kilogram of seawater and you added 1 milligram of CO2, it now weighs 1 kilogram 0.001. 1,000.001 grams, right? So really, the alkalinity is diluted a tiny bit by adding the CO2. But nobody measures it well enough to see that difference. So nobody usually talks about that difference. So this assumption is safe. This is a complexity of that choice of concentration scale. So what does this imply when we come to acidify seawater? Here's our picture. We're going to choose a seawater that's somewhere on that diagram and see how its composition changes as we acidify it. And we're going to acidify it to a pH of 7.3. So let's imagine we start with this seawater right here. An alkalinity of 2300, a pH of 8.2. That gives it a PCO2 of about 260. You can read the carbonate ion concentration again, a little bit above 225. We're going to acidify to pH 7.3. Well, there are two ways you could change the pH to 7.3 that people have used. There's numerous ways you could do it, but there are two that people have used typically. One is if you add CO2 to the system, and you will change the pH. The other is if you added something like hydrochloric acid to the system. So if we add CO2 to the system, it follows along that line. So although we might be changing the concentration in the gas phase and increasing the PCO2, as you can see, at first, for a small increase in PCO2, there's a very fast change in the carbonate ion concentration. And then in the later part, a slower and slower change in the carbonate concentration until we come to a pH of 7.3. And at that pH, the PCO2 would be quite high, 2,630. The carbonate ion concentration, fairly low, 37, with a saturation state of about 0.57. So saturation state well below 1. So you could imagine, because alkalinity 2300, salinity 35, this is the same water that you would find in the middle of the North Atlantic. Why do I say that? Because this is the canonical water chosen to be the standard seawater for salinity measurements, and an alkalinity of 2300 is the alkalinity it has and the alkalinity that's gone into the composition calculation when this is talked about as a reference seawater for the most recent definition of salinity in the thermodynamic definition from last year. So if you took a sample of that seawater, taken out of a few ampoules of standard seawater, this is the track it would go along. Well, people don't always do that. Sometimes they just add acid to get to a pH of 7.3. After all, the pH of 7.3 was what they thought was the important experimental variable. Well, if you do that, you go along a similar but diverging track. Essentially, adding acid, you more quickly reduce the carbonate ion concentration. And so it drops down quickly, comes through to this point here. They're both at the same pH. They're significantly different compositions of solution. PCO2 is about 20% different. A difference of 400. That may or may not be what you consider important to you, but it looks obvious. The aragonite saturation state is about a factor of 0.1 different. So although the pH is the same, although the salinity was the same, although the temperature is the same, Although you started with the same seawater, you ended up in noticeably different places. And so when you're designing an experiment to look at how a seawater composition change affects a biological organism, you should bear in mind that if Lab A added CO2 and Lab B added acid, part of the difference could be that they're not actually putting their organisms in the same composition as seawater. Of course, organisms themselves are sufficiently independent and separate from one another in their behavior that most of your problem is probably that and not the chemistry. But the chemistry you can fix. Another way to think about this is in terms of changes of alkalinity and of total carbon. So if we have a picture like this, adding CO2 essentially changes total carbon without changing the alkalinity. So that when we go back to this picture, coming down this red line, that's a line of constant alkalinity, about 2300. I could have drawn the same picture I did for total carbon for lines of constant alkalinity on this picture. But that really tells you that most of the seawater you will ever find is around that red line in a kind of thickish band. On the other hand, when you add a mineral acid like hydrochloric acid to seawater, you don't change the total carbon except by the dilution, that you've expanded the amount of solution you've got there. So if the acid's strong enough, you won't see much of a change. But you do change the alkalinity. So that, again, those two pictures here, essentially, the red line is a constant alkalinity. The purple line is following along constant total CO2. You don't end up in the same place. But I've made this impossible picture, which I will take a few moments to discuss, because it's taken the same sort of things that we had before and superimposed them now on that picture in terms of alkalinity and total dissolved carbon. First, the red lines, 180, 280, 500, those are the PCO2s. So that loosely, PCO2 is changing with these diagonal lines, getting higher and higher as we go to higher total carbon and lower alkalinities. Essentially, the PCO2 is roughly proportional to the total carbon to alkalinity ratio. At the same time, the blue lines are pH. And so people often use going to a particular pH as a convenient way of going to a particular PCO2. As you can see, the lines are not parallel to one another, so that's not really an ideal way of doing it. But again, you have the problem that we had in that original experiment, that if you just add CO2 or acid, in this initial part, the carbonate ion concentration changes very quickly, and then in this later part, a lot more slowly. And that's, in essence, because you're either going across this way or down that way. Just to give you one final touch, the green is where the aragonite saturation state is greater than 1, the yellow less than 1. So you can see that the line between the green line is another line that's not quite parallel. So the carbonate ion concentration is not so different from being parallel to the proportional to the CO2 or proportional to the pH, but not exactly. As a result, if you're coming down, changing the alkalinity, adding mineral acid, it takes you a while till you come down into that yellow region. You can go from 2300 across. Those are the differences. Well, why would you care? The way that I like to think about it is this, that realistically you should say, I have an organism and I'd like to expose it to such and such a composition of seawater. Where that composition, maybe you have a theory that changing the carbonate ion concentration will affect the calcification rate of the organism. In that case, it probably makes sense to explicitly target carbonate ion concentration values, not just pH. Once you know a carbonate ion concentration, you can say, well, how am I going to get there? Well, you have a number of possibilities, but one of the things you're condemned to is you probably only have one sort of seawater available. Here in Santa Barbara, it's whatever they pump in, appropriate, and that has a particular alkalinity that afternoon, which probably changes a little bit with time. And how do you get somewhere? Well, you can say, okay, I could just control the PCO2, this ocean acidification, that's what we're worried about. Well, you could, but probably if you're interested in an experiment in looking at calcification rates, you should choose the PCO2 to get you the carbonate ion concentration you want for that alkalinity, which is a matter of doing some arithmetic with the CO2 system. And there are programs that allow you to do this arithmetic relatively straightforwardly. They're all mentioned in that article I talked about. There's one called CO2 Calc, which for the ultimate in geekdom, you can put it on your iPhone. This perhaps is overkill. So the key is to decide where you want to be and then decide how you can get there. If the composition you want is different from the composition you have, how do you get there? Well, let's imagine you wanted to be here, and you are actually here. You're going to have to take out some alkalinity and add some CO2. That's how you would get there. The easiest way to do that is perhaps a combination of adding acid and bicarbonate. Why bicarbonate? Because it's much easier to add CO2 already dissolved in the water than to bubble it in to dissolve it in. So if you decide how much you're going to change it by, you can calculate the mixture that would have to be added to your sample and get it there relatively straightforwardly. And the way to think about that calculation is in terms of changes in alkalinity and changes in total carbon. Because alkalinity and total carbon can be thought of as components that can be mixed. So the mental picture is, where do I want to be? Where am I? What are these each in terms of alkalinity and total carbon? Even if that's not what I measured, then what would I need to add to what I've got to get to where I want to be? Go there. Then you can come to the second stage, which is, and how would I keep it that way? And there you might want to just control the PCO2 at a particular level to hold it there, because you will have changed the alkalinity to what you want it to be, and additional loss of CO2 is not going to change the alkalinity. So controlling the PCO2 is okay. Controlling the CO2 while monitoring the pH would work. There's all these possibilities. But as I said at the beginning, there are only two things you have control over. We can call them alkalinity and total carbon. We can call them pH and alkalinity. We can call them CO2 concentration and carbonate ion concentration. It really doesn't matter. You can only control two of them. That's at once the problem and the advantage that you have here. So the consequences, only two can be controlled. You cannot design perfect experiments to study organism physiology. The ideal would be to say, hey, I want to see how you matter, how CO2 matters to you. No, let's not clutter this up with bicarbonate and carbonate. It could be done, that could be done, but you'd have to be in an acidic solution. And mostly, the pH would be the thing your organism didn't like long before it decided it didn't like the CO2. So you can't design perfect experiments. So the plan is to choose the one where you at least get what you plan to get. If you know the seawater composition you have to start with and know where you want to go to, it's much easier to think about the changes as though they occur in total alkalinity and total dissolved inorganic carbon, because those are essentially straight line shifts on that plot. Whereas those shifts on the other kind of plot I showed you clearly have a lot of curvature. It's not straightforward to say, okay, how much PCO2 should I be going to? Should I be adding, changing? So for batch processes, you can change the alkalinity. For systems where you've got the seawater continually flowing through your tank, it's really inconvenient to change the alkalinity by any significant amount. And this is always going to be a problem, because I presume that here at Santa Barbara, as probably at Bodega and certainly at Scripps, the alkalinity varies throughout the year. So that if you have organisms growing and you always just put the local seawater in, they're necessarily exposed to changing CO2 conditions. How much does it really matter? Not as much as you might have feared, because a typical alkalinity off here on the west coast might be around 2200. If your alkalinity changes so that you can measure it, well, we can measure very easily changes of 5 or 10, 15, 20, 25, 30, 40, 50. That's still only just over 2%. Which means that if you're holding it at constant pH, the carbonate ion concentration will be varying by 2%. Or the PCO2, the CO2 concentration, will be varying by 2%. So although the alkalinity is clearly varying in a way that you can notice, it may not matter for the quality of your experiment. If it does, then you have to have a more elaborate system. But you should be aware of what the alkalinity actually is doing. The difficulty with the alkalinity, and you'll recollect the form of the equation, is that as there are more acid-base species present, there are more terms in this equation. And the terms are there in that equation even if you don't know which acid-base species are present. And so you can look at an alkalinity and say, is it changing, without necessarily knowing, can I interpret it accurately in terms of the CO2 system? And we'll come back to that discussion a little later when we talk in the second part of this about measurement of CO2 parameters. But I think it's important to recognize that you can indeed alter the alkalinity. You can measure it, you can alter it, without entirely knowing how to interpret it. And so that's the essence of my first talk today, to talk about the iniquities of the equilibria, the fact that this doesn't give you the total control you'd like over CO2 chemistry, but that all the pieces that you do know are related to one another by a fairly straightforward algebraic system. Thank you.